Okay, hello everybody, and hello Tom. So Tom, of course, is the inventor of RSpec, and I think it's an amazing piece of software. So, and I
Thank you.
want to take this opportunity to thank Tom for all of the things that he's done to make this class possible. Now,
Thank you.
this is an important session. You're welcome, Tom. This is an important session because we are just starting our final project. We are going to analyze a bunch of mystery stars. So I had the BARO telescope in a robotic mode on the 1st of September, and it imaged over 100 stars without me getting involved in it. Of course, it did take some pictures of the floor and some pictures of the telescope wall, the telescope dome, but most of the pictures were actually spectra. Almost all of them were usable. So we are going to be, and I've taken all of those. I made sure that the file name did not contain the the spectral type of the star. So I don't even know what the spectral type of the star is. We did a double blind ID on the star. So the file names has something called the BID, standing for blind ID. So you wouldn't know what the spectral type is, and I don't either. So our job is to actually go through the process that the scientists use, that a similar simplified version of the process the scientists use, using the principles of spectroscopy that you have already seen me talk about during our last session. That is about star types and luminosities and all of that. So we will be using all of our knowledge from that session in identifying the stars. So Tom has graciously agreed to be the student here, and he's going to drive the RSpec, and you will be doing the same process as he does. And Tom will also be adding some expert comments about the star itself and about the curves that you see and what we can learn from them. And he has a wealth of knowledge that I am just excited to see what comes up as we examine these mystery stars. So, uh, Tom, take it away.
Great. Well, before we get started, I just want to highlight one thing Chandru said. Thank you, Chandru, for all those kind words. Um, that scientists often are comparing a known to an unknown. And whatever field they're in, they drive a stake in the ground as a reference point, and then they look at unknown things and compare it to that. That's one approach. And we're going to see that here. So this is not just an exercise in clicking. This is actually following in the footsteps, not only the methodology that scientists use, but the methods that were used in the last century and before to learn about the stars and all the facts that we now know about their life cycles. So the first step, and the other thing, I just disclaimer, we're going to stumble around. I'm certainly going to stumble around. We're going to maybe have to redo things. We're going to try and get through this video without having to go back and do much editing, mainly for the sense of time saving for Chandru and me. And also, we want to keep it as short as we can so that you can get on with doing it yourselves. But the first step, and Chandru's going to chip in and just jump in, and we're going to interrupt each other and really have a good time with this. So bear with us.
Yeah.
So
So, Tom, one moment.
yeah,
I just wanted to say the session's goals are important. I just want to introduce the session before Tom starts talking. And the other thing that I wanted to say is I will be posting the actual Mystery Star video script that we use to produce this video, because that truly demonstrate a picture is worth 1,000 words, and a moving picture is worth even more. So,
yeah, and you can use that script that he'll um, post for a step-by-step guide on
for a
how to do
step-by-step
this.
guide.
Yeah.
Exactly. All right. So the
Okay.
goals of this session are to really determine or go through the process of determining a star type. That means we'll get some sense of what the color of the star is, what the temperature of the star is, what the luminosity of the star is, and also to provide input data into the final project, which is the Hertzsprung, producing the Hertzsprung-Russell diagram. So by doing this, and by identifying the star types of these 100 or so stars between all of us, we will create all of the data we need to populate our Hertzsprung-Russell diagram coming up. All right.
Okay.
Tom, you're on.
Okay. So the first step in all of this is the workbook that Chandru has provided you all. Chandru, do they have that already then? They'll have seen the
Yes.
screen?
So if you go to the BAROSpection website, and you will see, and Tom will start sharing a screen, you will see where all of this is provided.
Okay. I think I'm sharing my screen already. You may not have it visible on yours, but let's make sure I am before we...
It says Tom Field's screen, and I'm seeing you and me in the screen.
Okay. So let's stop screen sharing and I'll start it again.
Yeah.
Good of us to check. There we go.
Now we are sharing.
Okay. So this is the HRD data.
It is good that we were on there previously, Tom, with our beards and so on. So, this is truly a working session.
Yeah, we're in the trenches with you.
We're in the trenches.
We're going to go through the Nicholas data here and show
Before you do that, Tom, can you go to the main website, the BAROSpection website? Yeah, I mean, basically, the way to access details of the final project is to simply click on the news section right there. Yeah.
Great. Okay. So let's go to that spreadsheet. And each person next to the first entry with their name has a calibration star with the actual star type identified. And this will allow us to calibrate our instruments so that we can do this process. And so I'm going to just right click on this and select copy. And then I've got a Dropbox folder open here. And in Dropbox, I'm just going to come here and paste in that file, that star name. So that's the actual file name. And you can see there's a type identified there. And there's the folder it's in and the file. So we want to get this onto our computer. And so in Dropbox, I'll click on the ellipsis and click download. And I suggest, in fact, it's in the written instructions, that you create a new folder on your desktop that you will populate with this data. You can see I've downloaded some already, but I wanted to show you the first step, which is downloading this calibrated data. Chandru, any comments?
Yeah, and so this is an opportunity to download not only the calibration star, but all the other 5 stars that are assigned to you.
Right. So that would be all of these. You would copy the name and then search in Dropbox and then download them to your mystery file or folder on your desktop. Okay. Exactly. So the second step, major step here would be to start RSpec.
Yep.
RSpec will start out empty. And I wanted to give you a hint. I'm not sure I've even shared this with Chandru. Sometimes when we're using new software, it's not easy, hopefully, but we can get into a corner. We're not sure where we are. We just want to start from scratch, just clean everything up. This button here under Tools, this menu has a reset program to defaults. Hopefully you won't need that, but it's nice to know that you can clean things up. Okay. So we're here in the...
Tom, the one other thing we forgot to do was to download the instrument response file. So let's go ahead and do that, please. Yeah.
Yes. Thank you for reminding me. That's why 2 of us are doing this. We're both wingmen to the other. So we're going to come here, and okay, we're going to...
we go to the BAROSpection website, and there is a link for the instrument response file. And so click on the September 3rd. Yeah, that one.
Okay.
And then in here, you will see that there is the BAROSpection.
Thank you. Great.
Instrument response file.
Let's get that. I've put it in my mystery star folder once before, and now we've got it again. So now we're sure we've got the data that we need. So next is going to be, Chandru, to load that file, that calibration file that we just loaded, downloaded, which is this A05. This is a known star. And you might think, well, this is cheating. How do we get this bootstrap going? How do we know? Well, sometimes in a professional world, this kind of data is provided to you by the instrument owner, whether it's a JWST or whatever telescope it is. Other times you go through the calibration process like we are. We're just going to drag. Go ahead.
Yeah, well said, Tom. And then notice that the other files are truly mystery downloads because it does not show the type in the file name.
Right. This is the only one that has the type. These are all the unknowns.
Yep.
Okay, so we dragged it in here. Now notice it's at a little bit of an angle. Now you've seen this before. Just as a review, I'm going to click on the rotate button and rotate it around so it's horizontal. It doesn't change the results that much, but it changes it enough that it's worth doing. And let's see, I think I may have to go all the way around the horn on this one. No, it looks like just a couple of degrees. There we go. That looks pretty horizontal. That's good. Okay. So we'll bracket it in with our orange lines, right?
Yep.
And then we can close our rotate box or window. There's our flux. This is, again, intensity of the data in here, right? And this is in pixels.
Yeah.
So the first step is
so Tom, actually, let's change the precision. We need to change the precision.
Oh, thank you. Yeah. Got ahead of myself. Mm-hmm. So what did I do just there? I clicked on the gear for options. And then on this option screen, I came down here and made sure the precision was 2. That's just the number of decimal points we'll be using. It helps to have a standard there. Great. Next step, Chandru, is to calibrate, right?
Correct.
So we're going to do wavelength calibration. As a reminder, the reason this number is 3000 there is because our image is 3000 pixels across to this corner right here. So we're going to put enough information into the software that it can display angstroms here instead of pixels. So we click calibrate. And this is all in the steps in the document that you'll be getting, and you've done this before too. And then we're going to position ourselves in this first field and then come to the donut hole if there is one, right? We have a little donut hole because of our focusing. Just get approximately in the middle. We're not doing rocket science here or neural surgery. We just need approximate numbers. And this is the zero order, right? It's the star that just came straight through the grating. And then here, this is where we rely on our experience or some trial and error. We've had some experience. You've all calibrated an A-type star. And we know on our instrument, typically the hydrogen beta feature is here near the top. And so I was in this pixel field. I clicked there to enter that pixel value here instead of typing it. It's sort of a mysterious thing when you show it to somebody for the first time. They just see you here, and then all of a sudden there's a number there. So I want you to remember that it gets transferred over there when we click, unless we type it in ourselves. This is the hydrogen beta line. That wavelength is specific for a specific electron jump in hydrogen. And we're going to click on apply. Now, when I do that, again, as I mentioned, pixels is going to become angstroms. So now we're calibrated in angstroms. And if this isn't already checked on your machine, you can turn it on. The software is synthesizing the colors here. Remember, this is mono because mono cameras are more sensitive and more accurate. And this is the color spectrum. Now, one thing I don't know if we showed you, I don't want to take too much time on unnecessary features, but I wanted to show you, when you look at this, you can't really see any dimming in this from that feature, even though we can see from the curve that it's dimming. Let me show you why professionals use mono. Because look, now we can see all of those features.
Nice.
So this has to do with the way our eyes and monitors work with color. And color is prettier, so we'll leave that on for now.
Yeah, Tom,
So,
also,
yes.
you need to subtract the background.
Oh, right. Thank you. So now we're subtracting the background. Now, what that does is, let's just turn it off for a second. The skies by our BARO telescope aren't that dark. This area here looks black to us, but when we look over here, between the star and our spectrum, for example, you can see that we have a fair amount of light in there. It's not zero, which would be jet black. And so by subtracting the background, what we're doing is subtracting this area just below or just above the orange capture area to normalize, not quite normalize in a technical sense, just make this data a little more accurate to what was actually going on in the sky after the sky effects, the light pollution was removed. Okay.
Thanks for the wonderful explanation. I just wanted to say, Tom, that this action seems to be very sensitive to this process of determining star type. So while the calibration may not make much of a difference, but later on in the process, subtracting the background is really important. So make sure you do that.
Yeah, and Chandru and I have both tripped over that in the last week, forgetting to do it and then going, hey, how come it's not working? So hopefully you won't encounter that issue. All right, so now this is our key number. And this is a measure of how fast the spectrum is spreading out. That's a number you want to write down. It's also called dispersion, and that's going to be a number that's important to us as we go forward.
And so write it down right now, Tom. Why don't we take the opportunity to do that? So if you go to the...
right. Yeah. Go ahead.
So go to the global HRD sheet, write it down in the worksheet.
And that is 4.89. There we go.
Was it 4.89?
I think it was. Let's see. Yeah.
Yeah, 4.89. Excellent.
Okay.
And then, Tom, also, this is the opportunity to fill in the other fields.
Okay. We can, the magnitude of the star. Chandru, you've encoded that in the name here, 4.58.
Mm-hmm.
And the distance is 4.9 or 49.6.
Yeah, you don't need the decimals there. It is in parsecs, and 49 is good enough. And I also wanted to say that the yellow and gold fields are all the ones that I'm expecting your input. So when Tom entered those two numbers, note that it calculated the absolute magnitude of the star for you, and we will actually show the formula as to how that is done. Yep.
Yeah, and you'll be doing that in the class that occurs before this video is available.
Correct.
Okay, great.
Yep.
Just a reminder, and that is that the magnitude we see on Earth is affected by the distance the star is away from us. And so that's relative magnitude. And this absolute magnitude is a magnitude of, actually, I don't know. It's something about somewhere near the star, or theoretically how bright it is.
Yeah, it is 10 situated 10 parsecs away.
Oh, okay.
And that will provide a standard against which we measure what the intrinsic brightness of the star is.
Right.
And that's what the absolute magnitude is.
Great. Okay. So back in RSpec, we've now done the process of calibrating our instrument. We know this number. And that number, unless the grading gets moved, and it's glued in BARO, so it's not going to get moved, that number is pretty consistent. It should be exactly the same every time we do this. It varies a little bit depending on where we click things. But again, that those error bars, that little bit of inaccuracy, isn't something we're considering. We're really here more for learning than creating publishable data. Okay.
Maybe you want to show the hydrogen bomber lines.
Now
that we've done that. Yeah.
Sure. We pop up our elements screen and come down to hydrogen bomber. Now, what are the bomber lines again? The details are here. Those are the actual wavelengths. And I'm just going to put a check mark here, and we can see with a little bit of inaccuracy, this is the one we told it, but there's our hydrogen gamma. We can see a little wiggle there for delta, and there's our hydrogen alpha. So for our purposes, that's plenty accurate for us to do the kinds of investigations that we're going to do. I'm glad you suggested we do that. You went off script on that, Chandru. I'm glad
I did. I went off script.
Great. Okay. So next, what are we going to do? We're going to load a mystery star. Is that right, Chandru?
That's correct.
And which one are we going to load first from this data here? I don't remember.
All right. So I think we want to load the one with 4.67 magnitude. That one.
Okay. So there's that one.
It doesn't matter. We don't know what these star types are. We can load them in any order, really.
Yes. Okay. So let's go back to RSpec. there's my folder, and you said 4.67.
Yeah.
So let's drag that over. And then the steps that Chandru has in the script you'll get shows us dragging these lines into position.
Rotate if needed, and then dragging it into position. Yep.
Yep. Great. And this sort of looks the same, but we're going to see in a minute it's not. Mm-hmm. So the way the script reads now, it's a different process because we really don't know anything about this star. It's not an A-type star where we know where the bomber lines are so we can calibrate it and get this number. But since we already have this number, we do the 1-point calibration. Mm-hmm. So I'll come down here and click calibrate. I'll come up to this field here and put the 0 order in, which again is that in that donut hole. Let's take a look at that just for a second. I'm going to hold the shift key down on my left mouse button. It's a little messy, but clearly this has a hole in the middle, and so does this. So I'm just going to guess that the middle's here. It doesn't really matter. So it put that wavelength in. But we don't know anything else about this star. It's a mystery star. So we're going to use this 1-point calibration. When we do that, sometimes the software will fill in that number, that known dispersion. But if it doesn't, we type it in. That's the number that you put again right there on our A-type stars where we determined it. Anything to add at this point, Chandru?
No, that's the same number you'll use for all of your 5 stars.
Yep. So I'm going to click apply. And what it will do, actually, you'll see it do here, it's just going to shift this whole spectrum so that the 0 order is at 0 angstroms. And then I'll click close.
Yep.
We like the idea of clicking close when you don't need a window because it makes the screen less cluttered and maybe a little easier to get a sense for what's going on. Okay, so now we've got it calibrated in angstroms. And now what's next? Well, now we need to compare the shape of this curve to known stars. But before we do that is an important step. And that is that, I think you've already discussed this in various sessions, the camera sensor is more sensitive in green than it is in red and blue. It's more sensitive in this area, greens, than red out here or blue. Our camera, again, doesn't even pick up the X-rays out here or the infrared out here, but it does lose, as it gets out in these wings, it loses sensitivity. So before we can look at the shape of this, we need to adjust it. And Chandru has created that instrument response curve, which takes into account the camera, the grading, even somewhat the sky conditions. You know, if you're living near a forest fire, that sky is going to be a lot more red. So that would affect this end, the red end of the spectrum.
In fact, it will affect it from day to day. So this instrument response curve was created the same day the robotic, telescope took 100 spectra.
Right. So this is a new direction to take. Now, did they use this button already, Chandru?
No, they've never used it before.
Okay. There's a couple ways to do this. We've selected the easiest. We're not going to get into a lot of details. We're going to click on this color wheel. And here is a screen to correct for instrument response. Now, we downloaded that file earlier, so let's click on the ellipsis here, the triple dots. Go to our mystery star folder on the desktop. And there's the BARO instrument response file that Chandru and I then created for this telescope on that night. There's one final step to get this adjusted for our instrument.
So, Tom, there is a nice place for that window to rest. That is in the bottom right of the screen. Let's put it right there, and we can leave it there for the whole
great. Good.
session.
So I'm just going to click the apply button again. Watch how the shape of this curve changes.
Boom.
Wow. So that curve is the way the starlight actually hit our atmosphere before the atmosphere changed it and before our camera and before the star analyzer changed the colors a little bit. So now we're prepared to compare
and
this.
Also, the other thing I noticed, Tom, is look how bright the colors are now. Because, we've really adjusted for that, and we've limited all the other things that we do not get at the surface of the Earth.
Yeah. So now we're going to come over here to this
Tom,
reference
can I
button.
make
Yeah.
another point?
Oh,
So you
sure.
see those two vertical lines. So what we've also done is in this profile, we've completely eliminated anything that our eyes cannot perceive. So underneath 4,300 and greater than 7,300, we have completely snipped it off. So that means all of our calibration is going to be done between those two vertical lines. So that is an important thing for you to focus on. So we're not going to consider anything outside those two vertical lines.
And that's because our cameras get weaker and weaker in sensitivity out here. We wanted to use the best data we could. Okay, so now what we're going to do is click on this reference button and open the reference library. And we'll talk just a bit about this library. This library, if you want to read more about it, is called the Pickles Library. And you can view the original publication on the web under that button. And the thing that should be pretty exciting for you is that document was, and that research document, this reference collection, was created just 25, 30 years ago. So although some of the things we're doing are 100 years old, you're now starting to work with data that's closer and closer to today because you're getting more understanding and you're getting more sophisticated in the processes you're doing. So this lists the files, it's column by column. This lists the stars in temperature order. You'll remember that acronym that Chandru shared with you, OB and FGKM. OB, I don't like to use the gender specifics. OB, a fine goose, kick me. But again, fine guy, fine girl, kiss me also works. And as we click on these, the software will display on the reference curve in blue these stars from a professional telescope that has been carefully calibrated by a professional. And what we want to do is look for the one in here that most closely matches our curve. Remember, I mentioned earlier, compare an unknown to a known. Of course, our data here is the unknown, and these are the known. So let's do that. I'll click on this A05 star first. And you can see that, you know, within this visual range, there's really not a match there much at all.
Wow, that looks so different than the curve that we are looking at. Yep.
And do you notice that there's a lot of energy out here that's not even in the visible light range? That's because these very hot stars have a lot more energy that's beyond the ability for our eyes to see. And this certainly doesn't match our data. Well, let's go to the next one. And as we click through one at a time, and I'm going to just use my down arrow, and that's something you should keep in mind, that the down arrow key will let you scroll through this one at a time.
And as Tom is scrolling through that, I want you to make sure that you're looking only between the two vertical red lines.
Right.
Because so we are, even though it tells you a lot about what the star, where the star is radiating the energy the most, but we are focusing on the visible range only in determining the star type.
Great. Perfectly said. I love it. So I'm going to come up here and continue with my down arrow. Keep watching that blue curve. We're looking for it to be as close to that red curve as we can get. And as we're doing that, just to point out, notice this peak has started to migrate. It started over here, and now it's over here. And that's because as we go through this list in OB, a fine girl, kiss me order, we're moving into the cooler and cooler stars that have more and more red light over on the right and less blue light and X-rays and all sorts of high energy light. So I'm going to keep holding my down arrow key. Let's see, those curves still really don't match much. And we'll just keep going. And boy, that was looking pretty close, but let's just keep going and see if they get any closer. That looks closer. Now that's further away, and that's further away. Oh, that looks, well, I don't know.
Yeah, but actually it is further away because look at the peak that it created a gap, Tom. So if you go down a couple more.
Yeah. Oh, okay. Yeah, that gap there that I just drew, let's keep going down.
Yeah.
There we
go. So now we have a gap on the left. So to me, that doesn't look right either.
Yeah. So this is somewhat of a subjective process. There are ways numerically to do these kinds of comparisons. We're doing it subjectively here. Let's just keep going. What do you think about that, Chandru?
That looks really nice. I think we may want to write this one down for the moment, just briefly.
Yeah. So that's a G53, right?
Okay, G53.
I'm going to just keep going and make sure. Oh, and then something jumped, but oh, and that looks sort of close. Oh, I think that looks closer. That's
Let's write that
G84.
down.
So a G84.
4.
And let's just keep going. You can see that, well, see how these two lines are really close, but as we go one more star, now this gap opens up. So we're just trying to find lines. I think Chandru said in his document, we want them parallel without them crossing. It's the same thing. They're synonymous. It's good to have both terms. And now as we keep going, well, that looks pretty close too. That's a K star. So we know it's somewhere in the G and K range. It's not a hot A star or B star or A star. Let's just keep going with the down arrow and notice that now they're really diverging.
So now what is happening now, Tom?
Well,
you see, definitely it's crossing over, it's not parallel, but what does that mean?
So what that means is we're into the M stars here. These are very cool stars on the HR diagram. Most of their energy is in the ultraviolet and red region, right? This area, it's great drawing. This area here has much more energy. There's very little energy hitting the Earth from these stars in the blue or the green or the yellow. So we're seeing, this is called the shape of this curve. The technical term for it is spectral energy distribution. Is it more distributed?
Yeah.
Yes. Is it more distributed to the red end or blue end? And that tells us something about the temperature of the star. Much like with a candle, you may recall, I remember hearing as a kid that when I look at a candle flame, that blue part in the center of the candle is much hotter than that yellow part on the outside or on the coals of a fire. Same thing. And it's the same principle here. Red is cooler, longer wavelength light than the blue. Okay, so we've sort of scribbled down G8 or G5. And so I think this is a good point to go back and record our observations.
No, actually, no, Tom, because we wanted to actually go backward and see if we get a different number.
Yes. Okay, so we're out here. I'm going to use the up arrow now to go through the data. So watch for parallel here. Again, it's all subjective, but we're pretty good at seeing patterns as humans. Well, that's starting to get closer, but there's still a big gap on the left there.
And a crossover, which we do not want.
Yes. So we'll keep going. Oh, I went the wrong way. And that looks so close.
Yeah, doesn't it? I know. Yeah, that looks very close. Yep.
Yeah.
But there is a crossover though. I notice on the
there and down there.
Yeah.
Okay. So that's a K0.
Yeah.
That now there's a gap here. That's a G. So it's somewhere in this range. And now the gap's opening up here. And now that's clearly
so somewhere between a K0 and a G.
Yeah, some are K-ish, G-ish. I think I'm looking at these Ks here. A lot of these Ks look close to it. So I would say it's likely a K.
I think so too.
Okay, so we'll go to K0. And now, which is this in, let's go back to RSpec.
All right, so this was the 4.67, man.
Thanks. Yeah, so let's come back here. These floating windows sometimes burn through. So let me come back to here. 4.67, and we're estimating the type of that to be like a G0, right? Is that what we got?
No, I thought we said K0.
Oh, okay. Let's go back. Oh, I closed that window. So let's open it again.
Yeah, we need to take a screenshot also before we leave this.
Oh, really important. Yeah, I'm glad we came back. And so we'll come to the reference library. I think, you're right. K0 or G, somewhere in this range, lower Ks, upper Gs. Right. So you want to talk about the screenshot, Chandru? Yeah,
so the screenshots are important in my assignment. I talk about putting the screenshot into Slack as well as you will need it for the Jupyter notebook. And the screenshot should include the file name from the top so that we will know in the end to match the blind ID to the actual Henry Draper catalog number as we go through.
if I could draw well, I wouldn't be a programmer. But clearly I can, which is why I'm a programmer. Okay.
Yeah.
So, and we've now entered that information in I got
K0.
it again. K0. That's what I thought. Okay. K0. Great.
And
So
then
now
just go ahead and enter the two.
oh, sure.
Yeah.
I'm going to have to close this because it's burning through. And this is the visual magnitude is 3.9.
It's the wrong row, Tom.
Oh, so it is. Thanks. 3.9. And the distance is
No. The 4.67 is the
okay.
visual magnitude.
Oh, you're right. Yeah, I got them wrong again. 4.67.
And then the distance is 5.
Good. Thanks. Okay. So we've done here that mystery star. And you have 5 mystery stars to do, and they will probably be somewhat different star types, as you'll see as you go through them. And then you'll extend out here, and Chandru's going to, clean this all up, and you'll talk about how well you did and what sort of problems you had.
Now, let's just do one more this time.
Oh, okay.
We won't have much commentary, so people can just see what we're doing.
Sure. Okay. So I'm going to come up here. What was the second star we wanted to do? Do you remember?
The 2.44 magnitude, maybe.
There it is. Yeah. So I'm in my desktop mystery star. I drag this over. I'm now going to come back to RSpec. I'm going to move the lines around it. Look, you can even see those features in it. Some of you may even recognize this as familiar to your personal star that we selected. Now we're going to come up here to calibrate. And we're going to make sure we're positioned on line 1. And click somewhere in the middle in the donut hole to get that pixel value from down here in. We're going to make sure that the dispersion that we noted in the beginning is still entered there, and it will be in most cases. And then click apply, and you'll see this shift over to the 0. And now we're ready to do our comparison to the reference library. And I'm going to come back here to A05.
You still have to apply the instrument response, Tom.
Oh, thank you. Yes. It's so easy to get off course and then wonder, where did I...
It's already there. The window is already there.
Oh, you're right.
You.
Yeah, that's right. I usually have it up here. So I was going, where is it? Okay. So the same instrument response file, because the instrument response file is not star specific. It's specific to our instrument. So I'll click on apply. Watch the shape of this curve, how dramatically it changes when we remove the camera's insensitivity in the red. There's a lot of light in the red. Let's come back, and I'm going to jiggle these to get rid of this instrument response one more time. I know you didn't want a lot of commentary, Chandru, but look how as this data gets further into the red and then the near infrared and then the infrared, it drops. In real life, it wasn't dropping on the star. It was dropping because our camera lost sensitivity in this area. So our instrument response curve removes that effect of the camera. Now we can see there's a lot of red light in this star and not nearly as much relatively blue and green. Okay, now we're ready to use we'll put it here, our instrument response right here. I used that button for the reference library, not instrument response. I came up here to A05. Now we're just going to run through. You can see I can hold that button down, or I can use the down arrow on my keyboard. This moves awfully fast. Sometimes I overshoot with this, but sometimes it's helpful to get all the way out. Let's start here, and then I'll use my down arrow to go through the data slowly. So I'm going to come up. I think my down arrow didn't do anything. I think the down arrow only works when you're in that little display there. I'll be fixing that on the next release. So now let's step through and look for a curve that seems close.
So we're looking for an upward sloping curve.
Yep.
And not a crossover and between the two vertical lines.
That's getting pretty parallel. What do you think? We've gone past it now. Wouldn't you agree, Chandru?
Yeah, I think so.
Because there's a gap between the two all the way through.
But keep going just to see.
Sure.
Because sometimes it does jump up again.
Yeah. So you can see it moving further and further to the right.
Okay, so definitely not anymore. Yeah.
Yeah. Okay. And let's go back the other direction.
So it is a hotter star. We know that. Hotter than that.
Yeah. So
Yeah, so that looks great.
That's an M2, but let's keep going and see. That's a little crossovery. I don't know
Mm-hmm.
why that one jumped down, to be honest.
Mm-hmm.
And then there's an M1 that looks pretty good. And then I think it's probably, what do you think? M1 or M2, 3?
Yeah, so let's just say M2, and that's the
Okay,
average of what we've got.
sure.
Okay.
Okay, so we'll come back here. And again, remembering, because I never do, this is the magnitude 2.44. And we'll find that under Nicholas. And I probably went past it. Oh, this is one we grabbed from somebody else, I think. I don't see the 2.44 here. I
Oh,
forget. Oh, this is data that we dug up. You all have your own stars, but we
yeah.
wanted to make sure to show you this type of star. But
Hmm.
we would come in right here, wherever that star is, and we would enter our determination, which was it
Correct.
was M2.
Yeah.
And we filled in these two fields.
Yeah.
So at that point, you would have two of your stars done. So you
Yeah.
can see once you have the flow done, it's just a half dozen or a
If you
dozen
go back to
clicks.
Chandru, my example, you'll see all of them filled out. So
Oh,
that's what it would
there.
look like. Yeah.
Wow, look at
And
that.
you can you point out my estimated type and the correct type,
Oh,
which
there's a
I will
good,
talk
that's
about in just a
great.
second. Yeah.
So there's the estimated types that he did from pattern matching. And then the correct types are over here, right?
Yep.
And so by comparing those,
Yeah.
this you estimated G5 and it was G8.
Hmm.
Pretty good. This one let's go the same direction each time. You estimated it was an M star, it was a K, so it's a little off.
Yeah.
You estimated B, it was a B. This was a B8, B6. You can see we usually get the letter right.
Hmm.
And there's a G to a K, both cool stars off on
Hmm.
the right end.
Hmm.
G2, G2, wow, right
Yeah.
on.
Yeah.
And if this was his calibration star, so we'd expect those to match, which they
Yeah.
do.
So
So
Tom, can
go ahead.
can I press on you to do that star again, the B star, because I want to talk about B stars and how featureless they are. So go
Okay,
back to the Google Sheet and simply get that
good
number
idea.
from, yeah,
Okay, let's close some things down just so
yeah,
we are all on
so
the
that we're
same
ready to start
page.
over again. Yeah,
Yes, and I'll close the reference library. Not necessary, but it makes it clear for all of us.
yeah.
And now, which one was it? Was
Go
it the
to the
two?
Google Sheet and
Oh,
pick up,
Google.
yeah,
And do you want
and
to do
pick up
yours?
my B star. Sure.
Okay, that is this one.
Yeah,
Okay, I'll right click, I'll copy, then I'll come up here to my browser or my
Dropbox.
Explorer, go to Dropbox. Oh no, I want to
No,
go
you want to go to the
to
browser
yeah.
Dropbox.
Yeah,
Yeah.
there's two different ways to get the Dropbox, and I don't do it this way that we're showing you.
I
This is a
want
better
all of
way.
my students to go to the browser because the
I
search
agree.
window is a lot easier. Yeah.
Absolutely. I
Yeah.
agree. This is how I'm going to be doing in the future.
Yeah.
And then we'll download. I pasted the file name and we're going to download it. Is that the file? I just want to
Yeah,
make
that's
sure.
the file.
Okay.
Yeah.
And we're going to, again, I want to remember. Oh, there it's type A05. It's the MAG 4.58 star. Okay. So now we'll come back to RSpec.
Oh no, no,
And,
it cannot be that type. So clearly we picked the wrong one. So
oh,
can you go
okay.
back to the Google Sheet?
Oh, sure.
Yeah.
This is where it gets really frustrating for Chandru or anybody who's wingman and the pilot's flying all over the place and he's saying, no, no, turn here. So this is the one you want, right?
That's the one I want. So
Okay,
copy
maybe I
that.
didn't
Yeah.
paste it right.
Yeah.
So
Okay.
let's go back to Dropbox
Hmm.
and come up here and paste it. It's the MAG 4.48.
Yeah.
I'll hit the enter key. There it is.
There we go. Okay.
And now I'll download it.
Yeah.
And again, 4.48.
Hmm.
There it is. We'll come back to RSpec. We'll come back to the File Explorer. And we'll come to our Mystery Star file, folder. And there it is, the one we just
Yeah.
downloaded.
There we go.
And we'll drag it over. And we'll close this because we're not coming back there again in this video. And
Yeah.
now let's bracket it after we rotate it if necessary.
It looks good.
It looks good. And then I'll hit calibrate and I'll just select the middle of our donut and apply. Okay, take it away, Chandru.
All right. So now we have applied it. At this point, we have calibrated the star. Now we need to apply the instrument response, right?
Okay.
So
Yeah.
we do that by clicking the color wheel, and that put that window in the bottom right that you
And just
see.
as a reminder, if this doesn't happen to come in from your previous work, you can click on this ellipsis,
Yeah,
and that brings the same file in, the instrument response file that we've been using the
exactly.
whole time. Okay, we'll
Exactly.
click
And then
apply.
apply. Yeah, there we go.
Wow.
Yeah, that looks
That's,
very different than what we've seen before. Okay.
yeah.
So what this should tell you is, we've eliminated the everything beyond the visible range, but you will notice that this is a curve going up, meaning that it's a really hot star. And we may not be even seeing the peak wavelength because we've cut it off at the visible range. My guess is this star is radiating well beyond the visible range. And we will know that as soon as we put the reference on there. So Tom's going to pick the reference library and go to the O star. Okay, so and then let's keep going through and find a match.
Okay, I'm going to use a down arrow on my keyboard.
Down arrow.
Oh, we're getting close.
We're getting close. And only compare between the brown. So don't be confused by the little peak beyond the left vertical. Don't be confused by that. You're only trying to compare. It is still not quite parallel. So
now we've got a crossover here, so it's really not parallel.
So it's really not parallel. So let's keep going up. Going up. Okay. That's okay. That's it. So we are now. No, I think we have to go up further, Tom.
Okay, let's see.
Keep going up further.
Yep.
So those are all crossovers. They are not parallel.
Yeah, it's not matching as much as we'd like.
But the point here is this is where I want to talk about the fact that it is parallel, but it is rather low here. So go ahead and click on the cropped visible wavelengths right there.
Okay. Mm-hmm.
Okay. And then if you try it, you will see the parallelism a lot better. So in this case, it is really parallel. So my guess is this is where we are. I think so. In this case, you will have to use that cropped visible wavelengths to determine whether or not the two curves are parallel. Because go ahead and unclick that. You see?
Yeah.
Now you really cannot tell if they are parallel or not. But with that cropped visible wavelengths, it really gives us a guide.
Yes.
And so when you do that, look at that. So now you can even fine tune that a little bit to go up and down.
Yeah.
To create that parallel. There we go. I think that's where we are. It looks like a B star.
Yeah.
All right. And what was that? That was a B5
or so.
5. And if you go back to the Google Sheet, you will notice that I entered the actual star was a B6. So we did even better on my own to find it to be a B5.
Yeah.
Look at that. How amazing this is.
Yeah, it really is. And just as I mentioned, it's a subjective pattern match. And as you saw, they sometimes don't exactly match one another. But the early people observing stars, this is what they were doing. They were looking at these curves. We didn't really even know much about star temperatures. Yeah. But by comparing these curves to curves from red hot iron balls on the Earth and other objects heated to different temperatures, we were able to match curves and go, the stars are different temperatures, and here's how hot we think they are. The absolute determination of a star type, I just wanted to mention this, is done using these features. Yes. With a star analyzer, with this low resolution device, it's difficult for us to identify many features. I do notice, interestingly, on our star, we had an emission line here, but in the reference library, it's an absorption line. Those lines do look like they're pretty close to each other. I think they match.
I think they do. Something really interesting going on with the star. So we really need to look at the star. And the beauty of that is that when we actually identify the star, there is a decoding notebook that I've written. I'm not going to give it to you until you have your initial answers. It will lead us to a Henry Draper catalog, and we will find out a lot about the star. So to me, you're right, Tom. I think there's something very interesting going on with the star, and I'd like to find out what star this is, but I won't
Yeah.
reveal it because the Henry Draper catalog number is still not there.
I'm going to come up here. Oh, I don't know what the number is. I was hoping I could do my research. You'll
Oh,
have to
no, no, this one is done because this was my star. You'll
Oh,
see it right
okay.
there. I did
Oh, there it
decode it.
is.
There
So
it is.
let's go
Yeah.
look at it
It's Beta
online.
Piscium. It is in the Pisces constellation.
Uh, um, let's see. Oh, look at that. It's got emission
Oh
lines.
my God.
That's so cool.
We are doing science, everybody.
Yeah. This was not a setup. We hadn't
No,
discussed
no,
any of
no, it was
this.
not a setup at all.
That's pretty cool.
Yeah.
So again, some of you in your personal stars saw emission lines, and maybe that'll be discussed when you're all in a group after you've seen this video, and you can discuss why you think it might be. And that's a big hint for you. But
Right.
now we've detected with the BARO telescope and RSpec and your knowledge and some reference data from professionals. And again, I can't help but want to show you the original paper, because the first time you see a paper that's original and you can understand parts of it, it's very
Yeah.
exciting. Here,
It
this
is
is
exciting.
1998.
Yeah.
So it's a flux library with wide coverage, and it says there's 100 flux calibrated. That's the same term we use, the word instrument responds. This is a better term because it takes into account other things. All the normal spectral types. He talks about the star types and some reference databases. You're now using professional data to process your information. That's pretty cool. Congratulations to all of you who are doing this.
Oh, I think this is going to be fun. And the other thing is there is a possibility, albeit might be a remote one, that you might find something very interesting in these stars. Because imagine, this was only captured on September 1st. And I did 100 stars. Somewhere in those 100 stars, something interesting was going on, and we have captured it, right? Almost every spectroscopy course you will attend have boilerplate spectra that they've downloaded from somewhere. No, no, no. We have not done that. These are our own spectra that was
Yeah.
just imaged 3 days ago. So go ahead and mine these spectra. That is what this process was all about. I just wanted to say a few closing things, Tom.
Before you do that, let me
Yeah.
just, I want to just come back again, because we couldn't have scripted this any better to
Oh,
have.
yeah.
You watched a discovery happen. I was staring at this going, is that again, I'm always worried that whatever the problem is, it's my software and not the data. So, but that's the plight of being a software author, as
Yeah.
many of you know. But just to state this another way, we just saw in this abstract, and you can read through this. It gets pretty heavy and deep as you get further in, but these are normal stars, not unique or unnormal in any way. These are typical stars that he's included in his library. So the B5 2-star he included, because it's a normal star, has an absorption line right here at the hydrogen alpha. But the star that Chandru assigned himself, but some of you may also have stars like this, and unknowingly he assigned this unique star.
Yeah.
Is at the same spot. I'm going to hold Control and Shift down. At the same spot, we have an emission line.
Yes.
That's how discovery works. So again, I am just so excited for you to see live.
And Tom, I just wanted to make the point that we are only looking at a minority of stars that the robotic BARO captured on September 1st, because I've only assigned 5 stars to each of you. If any of you want more stars, I can give you another 5 more. And I tell you, there is something interesting going on in at least one or more of those stars that we might be able to find. So
we might, yeah. The one thing to point out is this: with a star analyzer, it is a low resolution device, and this number is down around 0.01 on professional devices. So they're looking at every little feature in here, and they know every little detail of it. So We may not be able to detect some of the new, unique science that's going on, but there's always a chance that you will. It could be something novel. Amateur astronomers have made discoveries looking at data just like this. So there's always a chance.
Tom,
Anyway,
I just want to say, well spotted. You made this session so exciting to see that emission line.
it's so neat.
So I just wanted to say, please take an interest in doing this. This is the real gimme for this. This is the real learning for this session. And then, of course, you're going to take these and plot it on an HRD and learn a whole lot more. I just wanted to say, once you do those 5, I will give you the decoding notebook that'll allow you to actually go and find out what the HD number is and learn a lot more about these stars. The sooner you do it, the sooner I can give you the decode notebook.
Yeah,
And
I wanted to say one thing, and that is, for 15 years now, I've had a vision of a course doing this kind of thing with data in RSpec from a star analyzer. And Chandru came along and on his own recognized that there was an opportunity here. And it's so exciting for me to see you all doing this. You are guinea pigs. I'm sure Chandru has different ideas about how next time he'll make some changes to make it a little better. But it's a great course now, and it really fulfills one of the visions I've always had for education in astronomy. So you're lucky to be there at the birth of something which I think, from a pedagogical, from an education standpoint, is brilliant and not evolutionary. It's a revolution in terms of people capturing data, their own data, and understanding so much about astronomy. So, Chandru, thanks so much for getting us across the finish line with this particular course that you've designed.
well, I mean, we are not quite at the finish line. We are at the 20-yard line because we still have to draw the HRD. But I think the biggest learning here, because that is more a Python learning exercise, I think the biggest learning here is what we have just done. So I just want to say we have actually done real science today. And this real science is more about the process than the end result, regardless of the result. Have you taken steps to, work on a repeatable process, and it's not just a random guess? That's number one. Number two, that you have recorded your observations somewhere where you can go back to it and look at it instead of you're not just watching YouTube. Of course, Tom and I are in YouTube, but you have actually done something beyond watching math videos and astro videos on YouTube. Just want to say congratulations. You can call yourself an amateur spectroscopist now. All right.
Yeah, you could even tell people that you've been doing some astrophysics.
Exactly. And it wouldn't be far from the truth. Thank you, Tom. Thank you for being our mentor, being our teacher, and producing this amazing software, RSpec, that allowed us to play with these things that our ancestors who drew these curves in whenever that was, you just mentioned, did it by hand. So this is so amazing. So thanks for that, Tom.
Okay, we done?
We are done.